So a lot of your work is now in developing tools to make data open and well documented, and also traceable and reproducible in the sense that you can go back to an actual exact state of a data set, but also with the addition of all the processing you can do on those data sets, and how the whole cycle of the management of those raw data to the processed data up to the results is actually done. I think so. It's got a very broad vision and very exceptional skills. Michael, I'm so grateful that you've come, and welcome. Please welcome Michael. This is the first version of this talk, so
exactly.
Very, very interesting and a premiere.
Yeah. Thanks for having me. And with that introduction, I first have to downscale expectations. So JP actually asked me to present something rough, not very well thought through, and potentially provoking, and make it short and leave space for discussions. Right. So this is more of what it will be. It's called a progress report because it is a snapshot of what we're doing at the moment at my host institution at the research center in Jülich, trying to actually roll out data management technology to an active research community that has other interests than participating in a rollout of data management technology. So first thing I want to make clear is that you've all heard about fair data, and I'm not going to talk about it. I think we've all had enough. Everything that I'm going to say is not in contradiction with fair principles in any of that, and we'll just accept it basically as a fact. What I do want to point out though is that in order to have a successful research data management, and here you can see a graph of something that's called that supposedly was derived from the Maslow pyramid, for those who are also in psychology. So oddly enough, this has been published by Elsevier, and what you can see here are the desirable properties of successful data that ultimately wants to become where's my mouse? Wants to become a reusable resource that can be used for reproducible research that is reviewed and comprehensible, and so on. So these are typically the data properties that you will get to hear about in open data and research data management talks. What I want to focus on is the other end of the spectrum, which we usually treat as a given. So data storage, where do we store it? How do we store it? In what form do we store it? And the next step, what do we preserve? And you can see even in the concept of the original authors, those are the gray parts. They're not worth thinking about because we have big drives, right? And there's still some Compute Canada somewhere that gives us half a petabyte, and we don't have to think about it much. But if you look at the data life cycle, the general flow of information from planning over data collection, collaboration analyses, storage and preservation comes relatively late in the process, but all the other pieces still require that data is somewhere. And so there is a lot more to research data management before we get to the point of deciding which aspects of data we actually want to invest further work in to make them fair compliant and better accessible and nicely structured input into or for reproducible research. And the other thing that you probably all familiar with from talks about this, including previous iterations of my own talks, is this depiction that the individual researcher is struggling with the management of their data. So here is the famous example of whenever you think as a researcher that something is final, there are at least 96 other steps behind it, and they leave a mess behind on your hard drive. And typically, the conclusion then is to say, well, the researchers, they're just not structured enough, and they have not insufficient technical capabilities. So what they should be doing is they should first become at least part-time software developers, because they have the tools, they use version control. And if we would all know version control, then the problem goes away, right? And I would argue that just saying people need to understand Git, and there are books about this, so they should read that, or the first half year of their PhD should be just technical skills, is a bit short-sighted. Because, you know, here you're in a more fortunate situation, but for example, in Germany, typical PhD lifetime or duration is 3 years, right? So that's not many minutes in 3 years, and every minute that you spend on technical education and software engineering practices is a minute that you don't spend on science, right? And then of course there's a trade-off between what do you want and how generic the skills are that you can take from one topic or the other for, you know, later career, potentially outside academia, but that's a separate issue. So I personally think that just focusing on introducing information, you know, version control technology to fix the problem is short-sighted. And to just make it clear, although we are developing DataLad and there is a version control system for data, I don't believe that DataLad on its own, or anything that it could do on its own, is the solution to the problem. And so if none of that actually is the solution to the problem, what is then the solution to the problem? Or why am I even here talking about this? And I think we ultimately need to decide, and probably not on a global level, but specifically for any institution or in a research environment, we have to decide how technical do we want the researchers to become, and figure out how much of the very constrained resource of time needs to be invested into what kind of topic. And then ultimately, how painful do we want to make it for researchers to participate in a process that gives us better quality data and you know, to some degree also better quality science at the end of it. And there are probably countless ways to talk about this. I found that I personally can draw much insight from asking the question whether my data management concept or your data management concept can answer the question, which data are important? And if you have had to do with, you know, any amount of data, then that question sooner or later pops up, right? Let's say you change your laptop, right? What do you copy? I would suspect that most people follow the same approach that I do. I just make sure that I get a laptop that has twice the capacity, and I just copy everything.
Yes.
Exactly. Is there anyone who doesn't do that? Great, right? So we're all on the same page. But that, of course, has issues, right? If we're talking about an institute that has, you know, computational aspirations, then we're at 0.5 petabyte at the moment, I think, easily. And if we're doubling that every 3 years, there are issues with that. And I think the question which data are important is a difficult question, because we have to look at it from various angles. And I could come up with at least 3 different roles or groups of people that would look differently at that question. And there's first and foremost the individual researcher that has some sort of goal, the career advancement, figuring out a particular scientific question, and so on. But there are also what I called data stewards, and they could be various different types of people. Those could be PIs that are, you know, sitting on top of, you know, larger research activity orchestration project. Those could be funders that invest money into research that is then carried out by individual labs. Those could be librarians that are interested in preserving meaningful pieces of information that have been produced. And of course, there are also there's the technical staff and technical administration, sysadmins, and people that design computational infrastructure or make sure that they are available to researchers. And I've, you know, listed here a few properties, data properties that I will not go over, but I just try to, you know, map what is interesting to those individual groups. And what you can see here, there are aspects like the unique nature of data that could be considered relevant for all people, for all groups. So we're all, for some reason or another, interested in not necessarily duplicating the work that has already been done. And you can look at that from a technical perspective, from a cost efficiency perspective, or from a career perspective, right? But there are other properties where the interest in them is not homogeneously distributed across groups. And for the purpose of today, I want to just stick with very, very low level, easily, in my opinion, comprehensible properties, which is, what kind of data do we want to invest our day-to-day resources like disk space into, right? Or what kind of data or what specific data sets do we want to invest in terms of long-term preservation and potential reuse? And thinking about all those things and being tasked with coming up with a scenario where we could answer those questions made me realize that that two aspects could potentially bring us to a situation where we can much easier make decisions regarding those questions. And those two I want to go over the next few minutes. One of them is modularity. And I'll explain what I mean by modularity. And the other one is ephemerality. So we'll go over them in order. And what I mean by modularity is that we need to have meaningful units of data that are clearly recognizable for anyone. And that is the key ingredient for us to be able to even understand what the what in what is important even is. Right? So if we want to decide whether some data is important, we need to know what that data actually is and what is, how much it, where it starts, where it ends, how much of it is there, and so on. And instead of belaboring that point a lot, I just want to give a quick example of how modularity can easily be lost or obfuscated in a typical scenario that I think we've all seen on file managers on our respective machines. So here you can see a very simple data set that maybe has two, let's say raw data acquisitions. They're called A1 in each of the two samples that are in here. Now imagine that's the raw data set. And in many systems and scenarios, if we would apply any sort of processing to that raw data, we could come up with a scenario where we put the generated outcomes or results or derivative data right next to those files, right? Because it makes sense. We could give them more comprehensible names and call them something something result or something something improved. But the point is we put them right next to each other. And I would argue that if we do this and just look at the content of those data sets, we have removed an important piece of information that is no longer easily accessible, which is which of that is the input to the transformation that whose output or which the output of which we've captured in that data set. So this infusion of inputs and outputs into the same structure in this very simple way is a problem, because now we need expert knowledge in the sense of what exactly was that transformation and what is the naming scheme, etc. That was applied. And I would argue that if we make a small change to this procedure, we would have an easier time and more accessible technology to make this problem not much of a problem or reduce its impact. And it looks like this. So here's the same raw data set that we've seen before, and we apply the same transformation, but instead of putting the outputs next to the files and infuse them into the same directory structure, we just keep them separate, right? And it's not important whether we call those inputs and raw, and it doesn't matter. But we keep them. We keep this part of the joint data set that has both the inputs and the outputs clearly separate, and we put them. We put it in a separate directory for a simple reason. And here I will make the first reference to DataLad, and I'll try to do that for the rest of the talk also, just to outline what kind of impact or how those design decisions could be used for technology that exists. So I'm not saying everybody should use DataLad, although I'm saying everybody should use DataLad, but there are clearly other solutions out there. The important point here is the idea, not the implementation. So in DataLad, we can treat those individual data sets as separate but jointly version-controlled entities, and they can be version-controlledly linked to each other. So what you can see here in that box is the full data that is necessary in a data set that references another data set in order to track completely the version and the availability information of another data set. And with this simple technology, which needs nothing else than a text file and a bit of code, we can use individually version-controlled data set to assemble pretty much arbitrarily complex analysis structure layout. So here's an example for a neuroimaging data analysis, which consists, if we're starting from the top, if I can see my mouse, here it is. We're starting from the top. So what you see here is a depiction of a, I would argue, relatively typical project folder that could exist on a laptop or on a compute cluster for a particular analysis, which is called analysis A here. And analysis A consists of particular code that makes uses some software libraries. This is documentation and maybe computational environments and so on. And this topmost data set, so all those little three-piece rectangular things, they represent individual data sets that are separately or jointly version controlled. This top-level data set captures the results of that analysis, right? And everything else, inputs to that analysis, they are referenced as the data sets that actually contain those data files. So they're actually not part of it. They're just placed in the right position to look like this in a traditional project folder. And that kind of nesting of data sets can be arbitrarily deep. So we can have the analysis reference a data set with preprocessed data, which in turn references a data set with the raw data that was the input into the preprocessing. And each level can also have the code and computational environments that are necessary or were necessary to computationally execute that transformation. Right? So we have here an indication of a data structure that not only holds the data, but in some sense also the provenance information of how the data came to be. And I would argue that if we modularize, we have made the first step to answer the question, what is important? Now the question is, next question is when to modularize. So what is a meaningful individual unit of data that we have to look at? And I came up with a bunch of reasons when you would want to modularize, meaning when you would want to put two files into two different data sets or two different directories if you look at it from the file system perspective. And I would say you would want to do that whenever the target audience for two files is potentially different. Right? So if we're looking at it from the neuroimaging data processing perspective, there are some people that work with raw data, right? Those are the pipeline people that pre-process a lot. And there are some people who work with processed data or pre-processed data or highly aggregated statistical information, right? Like metrics of some sort. And if you have two different audiences, then you would want to put those two files into different data sets. Also, if the target audience differs, in terms of who is authorized to see that kind of information, right? Public versus private data, different levels of protections, legal implications, and so on. And also the specificity of the information in terms of required domain knowledge in order to make any use of that information. So you can also use that as a criterion. Also, very important, if you look at it from a technical perspective, is the pace of evolution, right? So if two files are being expected to get updates at a different pace or for different period of time, then that's also an indication to put them into different data sets. For example, if I make an MR scan, the DICOM that comes out of the scanner is factual, right? It will never change, right? This is it. If it is broken, it will be broken forever. There's no change in information. The converted NIfTY file that comes out of it, because we make that because we decided that our entire software stack would not be able to read the original files, the DICOM files, is the product of a transformation that is potentially buggy or produce broken files, but can also be fixed over time. So we have an expectation that there could be an update. If we have that, but not for the other file, that's an indication to put them in two different data sets. Same goes for the longitudinal perspective of any sort of activity. So an ongoing study that will continuously see new acquisition, while each acquisition is factual and could be archived pretty much instantaneously, the study itself is something that evolves over time and needs a different data set that is more active for a longer time. There are technical constraints. So if we're talking version control, then nowadays we all mean Git. So Git has constraints in the number of files that it can deal with. So if you have a data set that has 1 billion files, don't put it in one Git repository. Just is not a good idea. It's a current technical limitation. Maybe it goes away in the future, but now it's an indication to put things into different data sets. You can have file system issues. We spent the last 2 days talking about the UK Biobank data set, which will eventually have 100,000 subjects. Most file systems that we're using nowadays will not be able to have 100,000 directories in any directory. It's just technically impossible. If you have that, you likely want to have the content spread over multiple directories, right? And of course, there are legal things that I already touched upon, where you can make data in one form available, but not in another. If that's the case, then you put things in different data sets. And then we'll essentially, separate what we talk about with data into more homogeneous subset of data in general. The other aspect is this ephemerality, in particular of workspaces, says that something is short-lived, right? So why would in a talk about data management technology you would want to talk about something that is short-lived? Because it's an interesting force that can be applied to change the somewhat social or psychological dynamics of the people working with data. So here's an example from my home folder on this machine. So apparently I have almost 1.5 million files on this thing, and for some reason there are on average 2 files per directory, and the oldest file is from 2004. That's my entire scientific career on that machine. And I have backups, so please don't steal this from me. Now the question is, if there is something like this, a data structure that I carry with me that I find really precious, for 15 years, what are the chances that this is organized enough that I could find the mental strength over 1.5 decades to not mess it up, such that I could give it to any of you and you could make sense of what is on there, right? I think we all agree that the chances are pretty slim, if not exactly 0, because I have problems understanding what is on there, right? And that's why I buy the hard drive with the that's twice the size as the original one, so I can afford not to think about it, right? But we are at a stage in neuroimaging and neuroscience research where we can't afford to not think about those things because there is real cost associated with it, right? And not all of us come from privileged institutions that can easily assign half a petabyte to an institute for people to just play with, right? So that is something that needs to be tackled in one way or another. So the question is, how can I get myself to not produce that mess and make it easier for others to understand what I did? And I think the idea of ephemeral workspaces can do wonders. So here's a schema of a data management or a managed data environment, a managed data processing environment that we could have. So instead of just having, so I use here this strange dollar something something notation to say that I'm not talking, when I say home, I'm not talking about my home directory of this laptop, but I'm talking about some personal workspace that people have. Where that lives is not really important. It doesn't have to be a laptop, doesn't have to be a workstation. It could be anything. Right? A rented cloud space, doesn't matter. But this is your personal environment, and what we consider personal, we would also consider this is the most flexible thing where we have the most degrees of freedom. We completely administer that ourselves. We can do whatever we want, right? We can be as clever as we can, but it doesn't mean that is clever in absolute terms, right? And I think if we are in an institutional setting, that is not for where do I keep my music files, but where the ultimate goal is that the research output that we produce is highly structured and interpretable, then I think putting a storage limitation on top of that to exactly make it impossible to just buy something that is twice the size and not think about structure, to take this liberty or privilege away. And also to have only minor computational resources associated with this flexible, unstructured environment. And then, of course, for any computational activity, there need to be compute resources, right? And you probably have a cluster here, and then there's a whole commercial industry that has cloud computing resources, and then there are high-performance computing centers scattered over the world. And those make analysis possible that we could not do on our laptops and whatever size personal devices, and they will give us a different set of constraints. So a high-performance computing center might allow us a particular set of a number of files, for example, or it requires a particular structure or data transfer mechanism to get information on there in order to be able to process them. And traditionally, this would be a communication that happens, from the personal environment to the computing resource, and then back and forth by some more or less structured mechanism. Right? Some people use batch batch handling, batch queuing systems. Some people not, and there might be a variety between them. Some people copy entire data sets, some only the parts that we need. So there's lots of heterogeneity, and as a consequence, there's lots of heterogeneity in the nature of the outputs. What I'm saying now is, and that's not revolutionary because it exists in many places, what I'm saying now, there should be a third component, which is just a data store. And a data store that enforces with no degrees of freedom how data is represented, and that is a proxy between the flexible home environment and the compute resource, right? So that in general, with exceptions, because we all need to make compromises in research, with exceptions, but typically information goes from the home environment into this highly structured data store, and the compute environment pulls information out of that data store. And what we have then, so the compute results are also pushed back into that data store, and for people to actually see them, they would have to pull them out of the data store again. So if we do that, then we have certain impact on the possible workflows that people can implement. So first of all, there should be very little impact in terms of the degrees of freedom that researchers have, for tinkering and exploring with data sets, because they still have their home environment, they still have some resources to explore data. But as soon as they want to do computing at scale, they have to use the machinery. They have to go through that data store. They have to structure the information in a particular way. And if we make all information transfer go through this data store, we can be sure that all relevant information, in one way or another, is in that data store. Right? So we have a single point that everything passes through. And if we structure that in a meaningful way, we have at least the potential to figure out the important part. Like, what is important? We have everything that there is in data. Now the question is, how do we mark it up so we can answer the question, what is important? And here's a DataLad specific part. So I'll just show you a flat file, no database required, implementation of a data store that has these purposes as far as I can see them at the moment. So you have a directory somewhere on a big hard drive, and it contains several pieces. So there is an entry for each data set. A data set, as we know, we modularize. So there's some sort of a more homogeneous part or collection of files. And each data set lives in a particular directory, and it's named based on an identifier that data set has. So in this case, it's a UUID, where the first 3 bytes form a second directory level. This forms a tree with 2 levels. This is only done to circumvent file system limitations to be able to store a few million data sets or even more in there. So in DataLad, every data set has a UUID, and it would look pretty much like this. The second part is underneath that directory, we store a bare Git repository that contains all the version control information for that particular data set. Right? So that's a directory that you can point a plain Git installation to, and you could clone the data from, and only then you would see the actual content of the data set. So here's a domain agnostic representation of that data set, which doesn't show us any of the files that it contains. Right? So if that data set contains a few billion files, we wouldn't care, right? Because they're not consuming a few billion files on that data store. So not taking away inodes unnecessarily. The third part is an object store for the actual file content. So for those, I don't want to talk about this, but DataLad uses a tool inside. It's called GitAnnex, which separates basically file content identity and the representation within a dataset. So any file, regardless of how big and what it was originally named, is represented as these kinds of things. So some sort of content hash that forms the file. In addition, we have a space where we can put archived versions of these object trees that we can compress and basically compress to a single file that is either internally compressed or uncompressed, different thing. And that's basically all there is. Right? So if that's the data store, the question is now, how would it look like for a researcher to use this machinery? And whenever a data set is created for whatever kind of purpose, people issue a command that says DataLad create, and this applies a particular configuration procedure. INM7 is the name of the institute that I work at, which completely encapsulate any setup overhead. Right? So a researcher doesn't have to know that there is this machinery in the back. All the connections for data transfer and so on, they're completely hidden behind that thing. Right? So that creates a data set that can now hold an arbitrary number of files. If people want to sync with that data store, the only thing they have to do is DataLad publish to INM7. Right? It's the name of the institute. So home could be their laptop, they could be somewhere. They just say DataLad publish to INM7, and the guarantee that they get is once their data is in the store, backups will be taken care of, data preservation will be taken care of, accounting will be taken care of, all those things, right? So they know whenever they reach a certain point where they want to make sure that this is preserved, they run this command, that's all they need to know. staging for high-performance computing systems or cluster, right? Now we have a completely domain-agnostic data store that can be interpreted in full by people who are not domain experts. So I can have a script that says, now move me everything that there is to this data set to the high-performance computing infrastructure. Or if that's complicated and requires credentials, I can simply say an email, say, please stage this data set. Why can I say that? Because each data set knows all its dependencies. So those other affected sub-data sets that are hanging underneath this data set, they can be programmatically discovered. And if they can be programmatically discovered, a machine can take care of this staging mechanism. And that is nice. So, and if people want to use a data set, as I explained, we always create a new data set for any outcome of a transformation. They just create a data set, as we've seen, they give it a name, and inside that new data set that they just created, they install another one that already exists, UK Biobank data set, HCP data set, whatever, and place it into a certain location inside the data set. This is all they need to know about the complexity and all the dependency handling, etc. Interaction with the data store is all being taken care of automatically by DataLad. So that is a gigantic black box that we can present to people that they don't have to worry about. But we know that black boxes ultimately come back and haunt you. So that is not the only thing that we're doing. The absolutely essential part for rolling out any sort of this technology to people who are not technical is the education. And it needs to come in two flavors. The first flavor is this one is an effort led by Adina Wagner. There needs to be comprehensive written documentation, right? And it needs to be targeted for people that are the primary audience for this. So there's a DataLad handbook that has about 300 pages at the moment, which is targeting first-year non-technical / psychology graduate students that need to be able to understand what this thing is doing to a degree that they can have confidence in what they're doing. And the second one is, and it has a second part. You can read it from the end if you're a PI or a decision maker and you don't care about the details. You just want to know which are the pieces that need to be plugged together in order to solve particular problems. So then you have a use cases section that is at the end. The second part is you can't just give people those books because you don't know whether they will read them, and some people will just have no meaningful starting point. So you also have to give them like hands-on training. So there's a course based on that book that can be run as a 2-day block event or as a series that accompanies some sort of a transition period that can present the juicy bits. For example, how can I with this system implement an executable or reproducible paper, something that you can download from a journal and compute, and at the end you will have the actual manuscript that was submitted to the journal from the raw data, right? Something like this. And I think I'm kind of late, so I'll quickly go over the last point. Whenever you do any of that, then you have to anticipate change. All the decisions that you're making will be invalid. It's just a matter of time, right? Storage technology changes, software choices changes, selection of software component might become unavailable over time. And you have to anticipate those things in order to guarantee a certain lifetime of your investment. One big point that we've already talked about over the last years is how much do you want to rely on external services that you don't control, right? If you're an institution like this, I would say you should not rely on external resources that you don't control at all because you can afford it, right? Some people can't afford it. What is absolutely critical in my point of view is that you have a consolidated representation of all the information that you consider a data set that lives in one place. For the single, or you can assemble one while the services that you're using are still running. And the single most important reason for that is you want to be able to transition to another service in the future, right? Services are fun, they look nice, you have buttons to click on, everything is fine, but those things will change, the technology underneath them will change. You want to be able to transition. And you want to be able to transition without reinventing everything from scratch, because it will be too expensive. And if it happens to you that it happens like 3 times in your career, you also look ridiculous, right? So you want to have the ability to transition built in. And then you really have to think about information longevity. So if you are running a data management system that deals with hundreds of thousands of data sets, you really, really want to make sure that those data sets don't contain stuff that needs frequent updating, because you want to be able to archive. You want to be able to still have the archived versions actionable for as long as anyhow possible, right? And I think if we can achieve something that still runs in 10 years, we can already be proud at this point in time. I don't think there is anything that still meaningful works after 10 years of time. In particular, information about the location of things that go into data sets. Whenever you encode a URL in one of those data sets, please, with sugar on top, make sure that you at least control the domain of that URL. If it starts with something that is not yours, it's already broken, right? That thing will go away. All your URLs will be broken. You have no way to install a redirector and fix things up. In DataLad, we have ways to have several levels of indirection. So you can, for example, say you can encode information in a data set. This information, this file blob identity, is available at INM7 storage. And then DataLad will call out to a program that runs on the machine with a particular name and say, go fix me this. And you can change that implementation on a machine, on a cluster, supercomputing system, whenever it is necessary, without having to touch all the 100,000 data sets that you created in the meantime. And Git is a decentralized system, so you don't even have the ability to push out reliably updates to all the various installations of those data sets. And then it's better to reference things by ID than by location, because those locations will break over time. Especially if you consider failure of institutional infrastructure, right? A computing center, it goes down, is replaced by another one, a storage appliance that is replaced by another thing, AWS for some reason changing the IDs of their S3 URLs, and so on. Yeah, things happen over time. So I think in combination, these two things allow us to answer some facets of the question, what data is important? Because in that data store, without having to have any domain knowledge, we can easily say which data has been recently modified, right? We can inspect those version control systems and simply say, what did happen to this thing in the past year, right? We can figure out the dependencies of any particular data set by just going through the list and figuring out what other data sets require this one. This can inform our decision what kind of investment to make for the preservation of a particular data set. We can look at dependencies for publication data sets. Like if you put your manuscripts in any of those data sets, their analysis results, the analysis results they're based on, will be tracked as data dependencies. So you can figure out which data sets belong to published entities, and you can treat them differently. You can also look for the contribution by a person. You can say, okay, this person has left this place 5 years ago. We no longer want to invest in the preservation of this information because we hate the guy, right? And you just figure out all the data sets and throw them away. Or do exactly the opposite, right? If you have a Nobel laureate, you want to put extra care in the preservation of those artifacts. So, and the key point is that all this information is available in that data store, and because you engineered the infrastructure to have people go through that data store for any meaningful or reasonably heavy computation, you have a chance of having an approximate estimate of exactly what is going on. And then with this one, I'll stop and acknowledge many people. Jarek, who's gladly sitting in front, who's the lead developer of DataLad. Joey, who is working on the underlying Git Annex tool. Benjamin, who's working with me. Kyle, who's working with Jarek. And Adina, who is the lead for our documentation effort. And at the moment, 22 additional contributors, which we are glad to have, and some of them are in this room. Thank you.